Okay, so now let's go back to deflection of beams, and where's my slide? I can't find it on my screen. Okay, so now for deflection of beams, what we discussed so far are the following. So we have the second order differential equation, which was discussed before the midterm exam. And then we discussed last Monday fourth order differential equation. And for today, we are going to discuss statically indeterminate beams. Now, in your mechanics of materials one, I would assume that you know what's the definition of statically indeterminate beams. So let's go to the proper slide, which is, actually, it's a sample problem. So first, let's focus on my notes right here. So if we have a beam, let's say cantilever beam, so we have a cantilever beam, let's say we have a distributed load, which we call W. Now, if we are going to determine the reaction at various points, we are going to get the following. So we can write the forces as this one. So we have, okay, let's put length L right here. And let's say this is point A and this is point B. Now, if we're going to write the forces on our beam, so this is going to be a W times L. So that's the length of the beam. And we have support reaction. So in this case, we are going to get support reaction at A along y-axis. We are also getting the support reaction at A along x-axis. And since this is a cantilever beam, we also have a moment. So let's say the direction of our moment is this way. So we have three unknowns in this particular case. So what are the unknowns? And take note that three unknowns, it's because your WL could be is usually given. So it's the value of your distributed load, and this would be the length of your beam. Those variables right there are normally given in a problem. Now, what are the unknowns? We have AY, AX, and M sub A. So our unknowns for this case are this three different numbers. How can we determine those different unknowns? So we can sum the forces along X is equal to 0, which gives us AX is equal to 0. And that's because we only have one force along X. And for your system to be in equilibrium, there should be a counter force. In this particular case, there's no counter force. So that's why A sub X is equal to 0. Now, you can sum forces along your Y. And if you sum forces along your Y, so you have AY, you have WL right there. And then you will get is your AY should be equal to WL to counter the effect of that loading condition. Now, how can we determine the third unknown, which is M sub A? We sum the moments, let's say, at point A, and then assume that's equal to 0. And then eventually, once you do that, you calculate all those moments. What you will get is MA is equal to WL squared divided by 2. And take note that this is 1/2, so this is simplified as, so this would be L over 2. So that's why you got this value. M sub A is equal to WL squared divided by 2. So everything is straightforward when you are calculating your support reaction. You should have mastered it during your mechanics of materials 1. Now, what do we mean by indeterminate beams? So let's say if we're going to add another support reaction at the end of this cantilever beam, so let's say we add a roller support at this point, this one right here. Once we add a roller support, we have another unknown. And that unknown is a force, B, or we can call it B sub Y acting along Y, which makes the system indeterminate. And if we are going to write that an indeterminate beam, an example of that, so let's change that to blue. Okay. So indeterminate beam, so we have the cantilever beam that we have this, and at the end, let's say you have a roller support. And now, if we are going to write the forces on our beam, what we are going to get are the following. So of course, there should be a load right there. Okay. So that's W. And then if we're going to write all the forces on our beam, That's this one is W times L. This is now force along B, so we call it B sub Y, and we have forces along our Y, which is at point A. So this is point A, point B, yeah, A, point B. So we have this, and then we also have A sub X because that's a cantilever beam, and we also have, let's say, a moment. Let's change direction here. So let's assume that this would be the direction of our moment. So that would be our beam. Now, if we sum our forces and moments, we are going to get the following. So say first thing is X. There's nothing really exciting about X because there's only one. So you can easily say that A sub X is equal to 0. So that's our first equation. Our second equation is about forces along Y. And if we do the forces along Y, we are considering these three things. So we have AY, BY, and WL. We sum them, and then we are going to get the following. So once we do that, we are going to end up with the following equation. So we have AY plus BY, both going up, should be equal to the force going downwards, WL. Now, that's the second equation. It's not conclusive. You don't know what's AY and BY. Now, we can sum our moment, let's say, at point A is equal to 0. So this would be our third equation. Now, once we sum the moment at point A, we are going to get the following. So I'm not going to show all the steps to save time. So you're going to get it's equal to negative WL squared over 2 plus BYL. And how did we do it? So if we sum the moment at point A, this particular point, so you have the moment which is negative, you have the contribution of WL, which is also in which is negative, and then the contribution going to B, which is a positive rotation, and you are going to end up with this equation. So now the problem here is whatever you do, you're going to be stuck with this one because you need 4 equations to determine 4 unknowns. And what are your unknowns? Your unknowns.
Excuse me, Professor. Oh.
Yep. Yeah, go ahead.
Cassie, go. You raise your hand first.
Yep. Go ahead. Yep.
Oh, sorry, Professor. I just had a question. In
Yeah,
your
sure.
moment of A equation, y is L squared, please?
Y is, sorry?
Y is L squared in our sum of moment at A equation.
Oh, okay, yeah, sure. So, okay. So it's L squared. It's because, yeah, they forgot to write it down because the distance of your WL is L over 2. So that's the half of the beam. So assuming that, yeah, I forgot to write it, the our beam with length L. So if you simplify your distributed load, it will be at the center, L divided by 2. So if you're going to get the moment at point A, so it's WL times L divided by 2, and that gives you this L squared.
Right, that makes sense. Thank you.
Yeah, no problem. Any question? And if I'm becoming fast, just let me know. Yep, go ahead. Yep.
Oh, just a small notation question. Is that some of the moments at P equals 0?
Sorry, it's A. Sorry, my handwriting is pretty bad.
I thought at first it was A, and then I wasn't sure.
Okay.
Thank you.
Yeah, that's okay. Yeah, sorry, my handwriting is bad. It could be better, but we're going to discuss it really slow. So, yep. But yeah, thanks for pointing that out. Okay, and again, sorry for my handwriting. Okay, so we have if whatever you do, you sum moments at B. You can always say, okay, I can sum moments at B, and I may be able to solve it. But in reality, if you check it, you'll get stuck with the same thing. So you cannot really deduce what's AY, what's BY, and AY, BY, and M sub A. So now you are missing one equation because you have 4 knowns, but you can only generate 3 equations. Now, how can we solve this type of problem if we are going to apply the concept of deflection of beams? Now, remember in deflection of beams, let's say if we talk about second order differential equation. If we have second order differential equation, we get C1 and C2 constant, right? Once we have C1 and C2 constant, we need 2 boundary conditions. So we need 2 boundary conditions to solve this 2 two different constants or constants of integration C1 and C2. So if we can get another equation from our boundary condition, we are going to get more equation out of it, and hopefully we can use the equations from our beam or deflection of beam in order to solve for our support reaction. So for this particular case, let's see how this is going to work. So let's go back to our beam, which is a cantilever beam and has a roller at the end. So now, if we have this particular case, what would be the boundary condition? And from our lecture, if we look at, let's say, second order, specifically for second order differential equation, and why did we highlight second order differential equation? If you go for fourth order differential equation, yes, you can solve it, but if you're going to solve it manually in the exam, you have four unknowns, C1 to C4, and then you have another four unknowns. So that could complicate things. So that's why we're going to focus just on second order differential equation for now. But yeah, you can apply it to the fourth order differential equation. Now, what would be the boundary condition for second ODE for this type of beam, assuming that we don't have this support reaction at the end? It's a cantilever beam, and we know that at A and B, so at X is equal to 0, the slope of your beam is equal to 0. Oops, dy dx. Okay, 0. So because it bends, the slope of your beam is 0 at point A. And take note, this would be at point A, x is equal to 0. Now, what's the other boundary condition? At x is equal to 0, your y is equal to 0. Of course, your y would not change because it's fixed at point A. Now, we use this two boundary condition in using second order differential equation because we only have C1 and C2. So for example, you can solve it using C1, you can solve this one using C2, and then you're ready to go. Now, if you have a indeterminate beam, you have this extra reaction at the end. So you can use another boundary condition, which in this particular case, and this is at point B, wherein at x is equal to L, that's the end of your beam from 0. At point A, it's 0. At point E, it's equal to L. That would be y is equal to 0. And it's obvious right here because at point B, it cannot go up and down. There should be no deflection at point B. It should not change. So this extra boundary condition can be used, or not directly this one, but can be used to solve some of the indeterminate beam problems. So in this particular case, you can have 6 unknowns. And what are the unknowns that we can get from that? So we have b sub y, a sub y. So you have a sub x. Oh, sorry, a sub x. Yeah, that's correct. M sub a, C1 and C2, because we are cutting
Professor, if you can simply repeat the last part, or just I'm having a little bit of trouble understanding if B, the point at B is a third boundary condition, or if it's just a description, because I understand that at x equals L, because of that support, y is going to be 0. It's not going to move.
Yes.
But is that boundary condition number 3? And does that associated with C3, or I'm just confused about that?
Okay, yeah. So remember that this boundary condition right here, it's a third boundary condition, and we don't have a C3. It's because it's second order, so we will only integrate twice. Yeah. So we can use that extra. So take note, this would be the extra boundary condition for you. Once you got that extra, you can use that in order to solve the unknowns from this top. Remember that after you calculated your support reaction, it doesn't make sense. I cannot get to a certain, like, a fixed value. I end up with a plus b is equal to WL. I end up with this. I cannot solve the problem, so I can keep this as it is for now. And then I can work on my second order differential equation and use this third boundary condition to add another equation. That makes sense?
I think so, yes.
Yeah. So you will see it once we do some examples, which we have here, that we are going to get. Because right now the unknowns are by, ay, ax, and ma, And we can only generate 3 equations out of that. So we can only generate 3 equations here. Now for C1 and C2, conventionally, we can only use 2 boundary conditions. So 2 equations to solve C1 and C2. Now that we have the third point or third boundary condition, we can generate 3 equations out of C1 and C2 or out of beam deflection, so that we're going to get 6 different equations. So we have 6 unknowns, and then we have 6 equations. And as you know, that's solvable. We have 6 equations, 6 unknowns, and it will be long, but of course you can solve those problems. Now let's try the example. I think we have an example, and I think we're going to see it much more clearly in this particular example here. So let's say we have this indeterminate beam, and again, how can we determine it's indeterminate? How can we check if it's really indeterminate? You have to check the support reaction at A. What are the support reaction? We have along Y, we have support reaction along X, and then we have a moment. So we have 3 different support reactions at just point A. Now, if you move to point B, you have another support reaction at B, which we can call BY, and we have 4 different support reactions. Now, once you have the system, once you have forces, X, Y, and moment, you can only generate 3 different equations. One equation from forces along X, one equation forces along Y, and another equation for your moments. So let's so in this particular case, you have 4 unknowns, but you only have you only have 3 equations. So let's try to solve this problem. So let's say we have A. And take note, there's a V right there. Just it should be Y. It depends on each book. They use a different variable, but that would be Y. And it's not Poisson's ratio for sure. So now, okay. Oops, overshoot that one. Okay, so that's the distributed load. And you can see this is similar to your midterm exam. You have a triangular distributed load. So you have points A and B. And you have length L. So you have length L right here. And then what else do we have there? A, B, length L. And this stop right here, we can call it W naught. Now, what would be the unknowns in terms of support reaction? So if we are going to draw all the forces on this beam, and right now I'm just assuming directions. So if I have that beam, I'm going to get A sub Y. So that's the support at point A. Take note, I have AX right here. And be particular with your exam. Even though A sub X is equal to 0, you have to specify that as well. So A sub X is equal to 0. And then your moment is, let's say, and right now I'm just assuming all the values. And as you know from your mechanics 1, I mean, right now we are assuming it, but if you plug in the actual numbers, it will just tend to self-correct itself. The moment could be the other way, or the forces could be the other way, but right now that's our assumption. So now we have B sub Y. Now, what are the unknowns here? So we have 4 different unknowns. Okay. So we have AX, AY, M sub A, and BY. And of course, I forgot the distributed load. Oh, I'll simplify this distributed load because we will calculate for support reaction. So if we are going to simplify this triangular force right here so that we can calculate the support reaction, this will be applying a force of 1/2. So that's the area of that triangle. So 1/2 W naught L. So it's applied 1/3 from this side. So if this is 2/3L, I'll change the color so it's more visible. Okay, it's purple. Okay, so right here, this part is L/3, and of course it's not scaled. 2/3 L. So So it's just the center of this triangle right here. So your 1/2 W naught L is being applied 1/3 of the length of the beam from point B. So let's go back here. So that's point B, and that's point A. Now, given those forces, we can sum the forces x, sum the forces in y, get the moment, and we can get some equations right there. And we can immediately see that it's not solvable, and we have to extend, we have to apply the second order differential equation, apply 3 boundary conditions to get 3 equation, but you only have C1 and C2, so that extra equation will be helpful to solve this problem. So let's try to solve this. So now, first thing is sum the forces along x, which kind of doesn't make sense for sure because everything will be 0, but it's important to point out that your ax is equal to 0. So now you solve ax, that should not be a problem. Now, if you sum your forces along y is equal to 0, you will end up with, so the forces going up, ay plus by, should be equal to the forces going down, which is 1/2 W naught, or I can sum it just to be consistent. Let's use negative 1/2 W naught L, which is 0. So now I can call the first one as, let's call this one as equation number 1, called 2, so that you can track it once you review your notes. So that's 1 and 2. Now I have the 2 numbers there. I can sum my moments, let's say at point B. So I'll sum my moment, point B is equal to 0. And if I sum my moment at point B, I'll get the following. So take note, I'm summing it from this part. So I'm moving B sub y. So I have 1/2 W naught L over 3, and that's the distance of this first load right here. Okay, minus a sub y. So I have my force at the end, a sub y, and that's for the whole length of my beam, and that's going clockwise, which is negative. The other one is counterclockwise, it's positive. And I have a moment, m sub a, which I assume to be clockwise, which I can write negative m sub a, and that's equal to 0. Now I can write it in such a way that it's ma is equal to something. In this particular case, m sub a is equal to W naught L square over 6, making sure it's correct, minus AYL. So now I can call this one as equation number 3. And whatever you do, you cannot solve AX, BY, MA, or any of these 4 unknowns. Now, how can we solve such problems? So now we can apply the second order differential equation. So we can cut our beam. And again, if you're doing second order differential equation, the first thing is to get m as a function of x, and then integrate twice. Integrate twice. So I'll just put here integrate twice. So our goal is to determine what's m as a function of x, and that could be obtained by slicing our beam and then determining what's the equation along our beam. So let's do that one, which you've done in your exam. Some of you got it correct, some of you are kind of wrong, but that's okay, and we can kind of discuss it here. So if I cut my beam, let's say, so I'll write the previous triangle here. So let's say it's triangle before and after. So that's the original size of my triangle. I will not write the arrows right now, but just assume that's your distributed load. And I cut a beam somewhere in between A and B. And if I cut my beam, so I would get this blue thing right here, blue triangle. And note again, that's distributed load. I just didn't put the arrows, but everything is going down. Now, what do you know so far when you cut that beam? Now, when we cut a beam, it has a certain length, x. X is anything between A to B, so that could be that would be x. I'll assume my shear force at the end of my beam, which is V, it's not 0 because it's in between A and B. And I would also have a moment at the end, which is M. All of those are just assumption for now, all the direction. And again, once you have numerical values, it will just self-correct itself once you plug in the numbers. Now, you have those assumption of directions right now. What else do you know? Now, I know that at this point here, this is the purple one. So this is W naught, and this is L right here. Okay. So this would be L. Now, remember in the exam, I mentioned bigger triangle and smaller triangle. What do I mean by that in the exam? So if I can call this one as WX, because that's after slicing at length X, I can say that W naught over L is equal to WX over X. So in terms of triangle, that makes sense because it's just the ratio between this length right here and this length here. Same thing for this smaller triangle. So which means I can get my W sub X. So if I get my W sub X, that would be W naught X divided by L. So this WX right here is W naught X divided by L. So that's also the same thing for your exam. That's how you cut beam in order for you to get the equation. So now I know that I have a small triangle with this value right here. This would be the value of this one. So now, if I'm going to sum the forces at this point, because that's how second order differential equation works, I can sum forces. In this particular case, we don't care about V, we care about M. So we can sum the moment at this end of the beam and get the equation M sub X, and that M is this M right here. So let's do that one. So once we get the numbers, we're going to get the following. So, and I'm going to explain each term one by one. So X over 3 is equal to 1/2 W naught X L X. So the first term refers to this force right here. So I'll get my smaller triangle. So this one is this one right here. Now this triangle has W naught X divided by L. So, and this is 0 right there. How can I determine the area of this triangle? It's 1/2 times, and this length right here is X. So 1/2 X times W naught XL. So that's the area of my triangle, which if you're going to look at this term, that's this W naught X and L, that's 1/2 and that's X. So that's area of the triangle, and that's acting 1/3 from the end of your beam. So again, this one right here is concentrating at 1/3 from the edge of your beam right here where we slice it. So that's why it's X over 3 right here. So that's the first term. And then if you check the so from here going sorry, from there, yep, going there. So if you check the direction, that would be a positive moment. So that's a positive number. So that's the first one. And the second term would be X times A sub Y. So we keep A sub Y as A sub Y for now. Where's A sub Y at the end of the beam? So we have A sub Y at the end of our beam. So that's length X. And that's a negative number because based on our assumption of direction, and you have to be very consistent if you're doing some assumption, and that would give you a negative number. Now, your moment, which we assume on the top, so if you will go up here, M sub A right here, we have M sub A, which is a negative number. So this equation has negative M sub A. And take note, it's continuous. It just doesn't fit in the screen. So minus M sub A. Now, you have a moment right here plus, because that's positive, M, and that's equal to 0. Now, if we're going to simplify it, so we have to get this m right here, and this will be the following. So negative w naught 6l x3 plus ayx plus m sub a. So this would be our m sub x equation. And this is the most critical part when you're doing second order differential equation, even fourth. For fourth, usually it's given, but for a second order differential equation, this is the most critical part, cutting the beam, accounting for all the forces. So any question at this point, how did we people. So we are going to discuss it on Friday. I'll check if I can upload it on Friday. But my strategy right now is I want to see first what's the problem in the class so that I can point it out during our tutorials on Friday. So before uploading it, I want to discuss it so that some of you will be kind of forced to attend so that they can see the solution. But I don't mind uploading it later. So yeah, I can upload it. Yep. Okay, so I hope that answers your question. But again, I want to discuss it. I'm going to have a look in your midterm exam probably tonight or tomorrow. Your TA will be correcting it. I'm just going to check what's the common mistake. Anyway, so yeah, so that's the m sub x equation. And now the objective is to plug it into our second order differential equation, which is sub y. And you have to be prepared for your final exam. That's why I'm doing it, because I know you have a lot of exams too. And if I upload everything, you might not attend, and you might not have enough practice for your final exam. So yeah, anyway, and tutorials is optional, but it's a good preparation for your final exam for sure. So now ei d squared y dx squared. So we're going to plug in that equation, which is w naught, and my handwriting again is bad, 6l x3 plus a sub y x plus ma. Now we have this equation and we can integrate it twice. So assuming that your m sub a is a constant, so we can now integrate twice. And I'll be fast integrating it. I'll just write it down. You can double check the numbers at home, but I'll just write the first one, which is dy dx is equal to negative, so that becomes x raised to 4, 24l x 5 plus a y, now it becomes squared plus now becomes max plus c1. I want to write down here c1. So now that would be our equation. So I forgot to number some of them, so I'm going to number this one. I'm going to go back, sorry, just to number it. So I'll call it 6. This one, I can call it 5 so that I can refer that. Once you check this notes, it will be real organized.
Should where you put x to the 5th there, should that be x to the 4th?
Sorry, yep, you're correct. Yep,
All
that's
right.
4. Yep. But yeah, my coefficients are correct. Yep, okay. And that's 3 from there, and then that becomes 4. Yep, sorry for that. Yeah. Y would be 5th. Yep. Okay. So now for just checking. So we have 1, 2, 3, 4, 5, 6. Okay. So now we can integrate this one again. So we have c sub 1. So if I integrate this again, and I'm mixing colors right now, which I really don't want to do, but yeah, let's stick with red. C sub y is equal to, so now this becomes 120L x 5. So now that becomes 5 plus a y over 6 x 3. And that's why I hate copying, because sometimes when I'm solving problems with you, I don't want to look at it so that it will be more accurate. If I'm copying, sometimes my eyes tends to look at different places and I copying the wrong thing. Yeah, hopefully this will do it. So okay, x squared plus, now this is c1x plus c2. So now I can call this one as equation number 7 right here. Now the first question is, what is C1 and C2? Let's not worry about the reactions right now. Let's proceed as we are solving a second order differential equation. So what would be C1 and C2, which are unknowns right now? We have two boundary conditions for cantilever beam. What can we assume for boundary conditions? At point A, at this point, we have x is equal to 0. So again, it's important for you to set what's x is equal to 0. In our case, that's on the left side. So at point A, x is equal to 0. And then we know that the slope at that point is equal to 0. Now, using this boundary condition, we can plug it in. Because we have a slope, we have to look at equation number 6 on top, because there's a slope right there. We can simplify the equation, so I can plug it into equation number 6. Now, if I plug it into equation number 6, let's take a look. I'm not going to write it down, but you can easily see it, that everything will become 0. So let's take a look at equation 6. This term will be 0. X will become 0. That will become 0. That will become 0. And there you go. C1 is equal to 0. I hope the exam will be that straightforward. But yeah, maybe. Yeah, C1 is equal to 0. So now we already calculated C1. We can now move to C2. So we can say at x is equal to 0. So let's just treat it as normal cantilever beam. Stick with point A, second boundary condition. So this would be, I can call it boundary condition 1, boundary condition 2. At x is equal to 0, my deflection at that point is equal to 0. Where's my deflection? It's at equation 7, right here, so that I can simplify the left side of my equation. Now, since x is equal to 0, and this is for most cases, if x is equal to 0, you can simplify a lot of things. So I'm not going to write the equation, but you can see here that your y is 0. This x here will become 0, and I'm pointing out in equation 7, this x will be 0, that x will be 0, that x will be 0, and that will leave you to C2 is equal to 0. So yeah, that's super easy. Yeah. So C2 will be 0. Now, I already solved the equation of my elastic curve, and I can tell whatever the slope of my curve between points A and point B, I can tell the deflection. But that's not the objective of what we are doing right now. We want to know what's the value of AY, BY, MA, and those support reactions. So in that case, we can use boundary condition number 3. And what's boundary condition number 3? That's the end of the beam, which is x is equal to L. You have y is equal to 0. Where should I substitute it? Of course, you can only substitute it wherein you have deflection, and that's equation number 7. We don't have any other choice but to substitute it to equation number 7. Now, if we substitute the values, assuming that we have C1, C2 is equal to 0, so both of them are equal to 0, we're going to get the following. So we have EI times 0, so looking at equation 7 from the top, is equal to negative W naught 120 L times L raised to 5 plus, we keep this one A sub y 6. Now your x becomes L, and then you have M sub A divided by 2 L square instead of x square, and then everything will be 0 out right there. So now by just looking at this equation, we can so this one would become 0. So we have two different unknowns here, which are AY and MA. So if we are going to go back to our calculation here, so you can go back here. So this equation number 3, take note that we have MA as a function of AY. Now we have another equation right now, which is MA. So if we go down here, we have now another function, which is MA and AY. So we have two equations, two unknowns for that specific AY and MA variables. So we can directly solve AY and MA from that equation. But let's simplify this equation first. So we can simplify this as MA is equal to W naught L square over 60 minus, and you can double check the math there, but that should do it. Oh, sorry. I think that's from equation 3. Yeah, I made a mistake there. It's not the one. So let's rewrite the equation 3. Yeah, I didn't simplify it here. Okay, so now we know that from equation 3, that's m sub a, we can now plug it in to that equation so that we can calculate for the values. So what we're going to get are the following. So, okay, I'm just checking what I did there. Okay. Yeah, okay, so that's spherical. Okay, so this is from equation 3, and this guy right here would end up with m sub a is equal to, yeah, I'm copying from the wrong page, minus AYL. So now you have two different equations, MA as a function of AL. I can equate both of the equations, so equate them. So if I'm going to equate them, I'm going to get the following. So
Excuse me, Professor?
Yep.
Isn't the equation that you just wrote the one that is from equation 3, not the upper one?
Yeah, so this is from equation 3. I'm going to pull it, recall. This one on the down is, the other way, right?
Yeah, I think you just have
it's the other way.
two mixed up.
Yeah, it's the other way. Yep. Okay. Yeah, thanks. Yep.
Okay.
Yeah, okay. Yeah, thank you for that. Yeah, okay, so this would be from equation 3, and yeah, thank you for pointing that one out. Yeah, okay, that's how bad my handwriting is. Cannot,
So
notes.
the other one, is that from equation 4? Or
so this
from...
so this one from the top, it's from the boundary condition on the so this MA right
okay.
here. Yeah, it's a simplified version of this. Yep. So I put A right here. So not to confuse you, and then I'll put it recall, so recall equation number 3 from the top. Yeah, it's okay. Okay, yeah. So now we can equate them because they are both m sub a. So now W naught L square over 60 minus AYL over 3, and that's equal to W naught L square over 6 minus AYL. Now, you can see that we only have a sub y here, a sub y over there, so you can easily calculate a sub y, and a sub y in this particular case would be 27 over 120 W naught L, 9 over 40 W naught L. So that. Okay, yeah, okay, yeah, so that would be the value for AY. Now we have AY, we can substitute back AY to our MA, and then we can calculate for that. So substitute AY, which is this on the top, to equation 3, let's say. It could be equation 8, could be equation 3, you should get the same. So now you will get m sub a is equal to -7, and you can do this as a practice at home. So you're going to get this m sub a right here. So now you know m sub a, you know a sub y, you don't know b sub y yet. So you are still looking for b sub y. And if you go up to your equation, and I'm going to scroll it right here. So now this equation, number 2, so you have AY, you have BY. Now I can calculate for my BY using equation number 2. So I can recall equation number 2 for my BY. Call number 2. So if I recall number 2, that's AY plus BY minus 1/2 W naught L, and that's equivalent to 0. I can substitute my a sub y, and that would give me, let's do this slowly, 9 over 40 W naught L plus b sub y minus 1/2 w naught L is equal to 0. And that would give me a value of by is equal to 40 w naught L. So now I already calculated my by. Now, how can I summarize that one? So now I have my ay, which is 9 over 40 w naught L. I have my by, which is 11 over 40 w naught L. I have my output ax first, which we calculated as 0. And we have m sub a, which is equal to negative 7,120 w naught L square. And we have C1 is equal to 0, C2 is equal to 0. And those are the 6 unknowns that we calculated for this particular problem. Any question at this point? Any question? Any question, class? Everything is clear? Okay. So now, so that's the method in order for you to calculate for indeterminate beams. Now the next topic will be singularity functions. So and we still have 3 minutes, but yeah, probably I can dismiss you early right now. But for singularity functions, we're going to discuss it on Friday. And I'll just go back to the slide. So, oops. So I know that from previous meetings, I mentioned that I'm going to leave out method of superposition. I calculated the time up to the end of the term. I think we can cover this one on Monday. This will not be included in your quiz number 4, but this may be included in the final exam. I haven't decided for the problems yet for final exam, but for quiz number 4, it's just up to whatever we're going to discuss on Friday, which is singularity function to determine slope and deflection. Any question, class? So I'm going to stop the recording and I'm going to dismiss you 2 minutes early right now.